Great, so welcome back to day 3 of the Zurich Homology Conference. Our first talk today is from Arik Wilbert. The title of this talk is Kovanov Homology, Arc Algebras,
Yeah, thank you very much. It's a pleasure to be here. So I have to say that some of you have seen a talk which is similar to this one just a couple of weeks ago, but I tried to say some new things. So this time I have slides, so maybe I'm a little bit faster so I can add some things. So we'll see. Okay, so right, so I want to basically start by recalling the construction of Khovanov homology quickly, and then I want to say what's different when you move to what's called odd Khovanov homology. So the first thing I have here is a diagram of a link. We have this Hopf link, and what we want to do in Khovanov homology is assign a chain complex to this, which will be an invariant of the knot or link. So let me briefly recall the construction. So someone gives you a link like this. So what you usually do is you label all of these crossings by a number. So this is, let's say, the first crossing, this is the second crossing. And then what you want to do with these crossings in the first step is you want to resolve them. So here is a crossing, and there are two ways to resolve them. So I can either do a 0 resolution or a 1 resolution, and the corresponding pictures are up here. Okay, so now if I do either a 0 or a 1 resolution at each crossing, so what happens is I get this cube, which I think most of you are familiar with. So what happens here is, for example, let's look at this first picture, which is labeled by 0 and 0. What this just means is that I looked at the first crossing here labeled by 1. I performed a 0 resolution locally where the crossing originally was, and then I performed a 0 resolution at the crossing labeled by 2. And the resulting picture is just 2 circles in the plane here. And something similar actually happened here. So for example, in this picture, I did a 1 resolution at the crossing labeled by 1, a 0 resolution at the crossing labeled by 2. Here, there's a 0 resolution for the crossing labeled by 1, a 1 resolution for the crossing labeled by 2. And then here I have 1 resolutions for all the crossings. So what I can do then is I can arrange all of these, what people call complete resolutions, in a cube like this. So what I mean is basically I arrange all of these complete resolutions in columns. And so the first column has all the pictures which contain only 0 resolutions. The second column contains only pictures which have exactly one resolution. And the ith column kind of contains all the pictures which contain exactly I1 resolutions. And in general, you get a big hypercube. So here, this is just a square, okay, since I only have 2 crossings. So then another important thing before I can actually turn this into a chain complex is I have to introduce certain arrows and connect some of these pictures by arrows. So what's going on here is basically I look at 2 pictures and I'm going to draw a arrow from the first picture to the second picture whenever exactly 1 0 resolution changes into a 1 resolution. So for example, if you look at this arrow up here, what you're getting is an arrow from this picture labeled by 0 0 to the picture labeled by 1 0 y, because this first 0 resolution changed into a 1 resolution and nothing else changes. So this is indicated by this labeling here, *0, that just the first resolution changes from a 0 to a 1 resolution. And this is when I get an arrow. So for example, for this arrow here, the second 0 resolution changes to a 1 resolution, nothing else changes. For this picture here, I just changed the 0 resolution to a 1 resolution, so I get this arrow, and then there's an arrow here as well. So this is how I can construct a cube of certain pictures. So now the question is, how can I construct a chain complex for this? Well, I have to assign something to circles. So this is step number 1. So whenever you look at a picture like this and you have n circles, you assign to this quotient of this polynomial ring in n variables. So this number n here, the number of variables, corresponds to the number of circles. And then I mod out by this ideal generated by all the variables squared. So what people usually do is they do this in a graded setup. So you usually put the generator xi in degree 2. But for the purpose of my talk, I'm not going to really keep track of the grading. But for the purposes of categorification, as you know, this is you have to do this, or you lose the Jones polynomial in the process. And so then, once I know what to put here for each vertex in my cube, I have to do something with these arrows, and this is described down here. So if you look at the combinatorics of these pictures, whenever you have an arrow connecting 2 pictures, what's actually going to happen is that either two circles merge. So this is exactly the situation here for this arrow. So you have two circles and they turn into one circle once you switch the 0 resolution to a 1 resolution here. Or the alternative would be that this one circle splits into two. So these are the only things that can happen if you look at this from a combinatorial point and think about this for 5 minutes. So what I need to do is I need to assign maps between these scores of polynomial rings whenever two circles merge or one circle splits. So for the merge, so this is what I wrote down here. So let's say the ith and jth circle merge and become the kth circle. So what happens in this case is, well, I'm moving from a polynomial ring in n variables to a polynomial ring in n-1 variables because I have one less circle, right? And the rule here is to replace every xi and xj by xk. Okay, so you just look at let's say a monomial in here, and you just replace every xi and xj by xk, and then you view this as an element in here, and you get the result that you want. And then there's a similar map for a split. So here the k circle splits into the circle labeled by I and j, and then of course I'm gaining one circle. So this is now going from a quotient of polynomial rings in n-1 variables to a quotient of polynomial ring in n variables. And here the rule that I want to use is I want to replace all xk by either xi or xj you choose, doesn't really matter. And the result gets multiplied by xi plus xj. Okay, so this may be a slightly awkward way of just saying what you know. I mean, you can basically get these maps by applying a TQFT. But for the purposes of this talk, I thought this would be the most convenient way to write down these maps. But these are literally the maps that you get from the TQFT associated with the Frobenius algebra given by the dual numbers. So just a slightly awkward way of writing what you probably know. Okay, and then the last step is kind of to make all of these cubes here, or the facets of the cube anti-commute. So you sprinkle some signs here in the construction, and then you basically sum along the columns, take direct sums of these vector spaces here and direct sums of these maps, and you actually get a chain complex. And then given these orientations here, there are certain shifts that come into the picture. And this is indeed this KHD, the Kovanov complex of this knot or link diagram. So this is the well-known construction. So what I want to do now is modify certain things here to get to what people call odd Kovanov homology, which is sort of the purpose of this talk. So what's going on here is basically I want to replace the vector space at each vertex by an exterior algebra. Okay, so as a vector space, so this exterior algebra generated by n variables here, this is going to be the same as this quotient of the polynomial ring. But something interesting is going to happen because variables here do not commute. Okay, so in this blue version, with the exterior algebras, variables do not commute anymore. So whereas the original Kovanov homology is somehow commutative, I want to think of this odd Kovanov homology as something non-commutative or something that's just commutative up to signs. Okay, and then the construction is kind of similar. So you just put an exterior algebra at each vertex, and then you have to modify these maps, of course. So let me tell you how to do that. So let's replace the merge map by a map between an exterior algebra on n generators to an exterior algebra n minus 1 generators, and you see the rule still remains the same. Okay, so this is why I kind of phrase it in a slightly awkward way. So it's still the rule, well, you take a wedge of like these variables and you just replace xi and xj by xk, and then you view this as an element in this exterior algebra n minus 1 variables, and you're done. Okay, so the interesting thing actually happens with the second map, the split map. So let me change this. So now I have an exterior algebra everywhere. And now what you see here is there's actually a sign coming into the picture, which makes this construction actually non-trivial and interesting. So you still want to replace every xk by either xi or xj. That's exactly the same rule as before. But if I don't know, I am in this room and you go to the next room, and let's say I replace xk by xi and you replace xk by xj, we're going to get different results. Okay, so in order to make this well defined, I have to introduce this sign here between the variables. So this sign here. And now you see there's also a choice, right? So one of these variables needs to get a sign. So they need to have opposite signs in order for this operation to be well defined. So there's some choice here coming into the picture, whether I want to have the first variable labeled by I positive or the second one positive. And this is what's going on. So in some sense, what you need to do now, if a circle splits into, let's say, the i's and j's circle, you have to give some circle, you have to make some circle a preferred circle. Okay, this is the guy that gets the negative sign. So what happens here is something new happens on the level of these maps. Okay, but once you're done with this, you can do the same construction. You still have to sprinkle certain signs, and you sum along the columns, and you get what's called odd Kovanov homology. So it's pretty much the same story as before. But it is actually quite interesting. So let me summarize some things here in this theorem. So the original construction is, of course, due to Kovanov, and then this odd version is due to Osváth-Rasmussen-Szabó. So first of all, these constructions actually are link invariants, right? So the homotopy type of the chain complex that you get both in the even version and the odd version, they are indeed link invariants, and they're independent of all choices, meaning independent of the sign assignments and how you label the crossings and all of these things. And they both categorify the Jones polynomial, which is maybe not so surprising given the fact that the underlying vector space is the same in both construction. So the only difference is actually in the maps where I introduce these signs. And since it's only signs, also maybe bullet point number 3 is not surprising. So mod 2, these things actually coincide. But now the interesting point number 4, is actually that they are very different. So it turns out that actually the odd Kovanov homology can distinguish certain knots and links which the original Kovanov homology cannot distinguish, and also vice versa. So you really want to actually look at both. So there are two different link invariants, which is quite interesting. Yeah, so this is the basic setup. So maybe, does anyone have any questions about this? Yes. That's a good question, and I don't know the.
Can you repeat the question, please?
Oh, the question was about S invariant for odd Kovanov homology, and I don't know the answer because that's too topological for me. There isn't? Okay.
Yeah, so the reason for Reshetikhin-Turaev's chronological coordinates was trying to do family theory, but didn't. So, like,
oh, I see.
There's no odd.
Yeah. Okay, so Melissa, maybe I should repeat this. I don't know if you guys heard
Yes.
this. Did you hear it?
No.
So, oh, yeah. So Melissa said basically, so what happens here is you can describe this odd version using a TQFT as well, in which case you have to use chronological cobordisms. And people were trying to get some kind of Lie theory for the case of chronological cobordism, which is the underlying cobordism theory for this odd Kovanov homology. And apparently they failed, which is the problem why there's no S invariant. Is that right?
Yeah.
Okay. Yeah, so this is, I guess, a good answer. Okay. So anything else? Okay, so then, yeah, let's move on. So here's a general question that I'm interested in, because I am actually a representation theorist. So what I want to do is I want to extend Kovanov homology to tangles. And the reason is, this is when you actually see some interesting representation theory. And the representation is kind of degenerate if you just look at, yeah, the original Kovanov homology. You really want to look at tangles. And this was actually done successfully. We can extend Kovanov homology to tangles. And there are several constructions, like the combinatorial ones due to Kovanov and Chen-Kovanov. There's a Lie theoretic version by Stroppel, and there's a version using coherent sheaves by Curtis Kemser, many more. So I just listed some that fit my bias, so to speak. Right, so I want to explain one version of this, namely the one which is due to Kovanov and Chen-Kovanov. And this is where these Arc algebras come into the picture, which also appear in the title of my talk. So there's an Arc algebra here, which is a certain unital associative algebra for every n, for every natural number n greater than or equal to 0. And yeah, these were originally constructed by Kovanov, then generalized by Chen-Kovanov, and then vastly generalized by Stroppel and Braden-Stroppel, in which case you actually get very interesting connections to representation theory. So at the end, the plan is to actually say something about this. So we'll see how far we go. So I really want to explain this algebra here real quick, because this is the key ingredient to do this generalization to tangles. So there's one combinatorial tool here, and this is a set of crossingless matchings. So I'm going to denote this by Bn. So Bn is a set of all crossingless matchings on 2n vertices. So what does that mean? So what I'm going to do is I'm going to fix a horizontal line here, and I'm going to fix 4 vertices here on this horizontal line. And what I'm going to do is I'm going to match these vertices by connecting them pairwise by an arc, okay? So what happens here is essentially, yeah, every vertex has to be connected to exactly one endpoint of a cup. And the important thing is, of course, this crossinglessness. So I don't want these diagrams to cross. So maybe let me try if I can write something. Oh yeah, this actually works. So this is, for example, forbidden, right? Because yeah, this is a diagram which has crossings, and we only want to have crossingless diagrams. If you look at crossingless diagrams and 4 vertices, these are the only 2 options that you have, okay? So this is the basic diagrammatics, and what I'm going to do now is I'm going to build an algebra out of this. And the first step I'm going to do is I'm going to pair these diagrams. So I'm going to take one of these diagrams, take a second one, and then I'm going to rotate one or like reflect it across this horizontal line, and then I stick them on top of each other. So here I paired the first guy with itself. So here's a different example. Here I get this peanut by pairing the second diagram with the first one. Then here is basically the first one is the second one. And then the last possibility is literally the last one with itself. So here I have these 4 possibilities. So now how do I get an algebra out of this? So the first step to get an algebra is to get a vector space. So what I can do is now I can basically yeah, look at these configurations. They're always just a collection of circles, right? And I can just do the construction that we know from Kovanov homology. So I count the circles and I assign to this a quotient of a polynomial ring in the respective number of variables, like corresponding to the number of circles. So the first one is a quotient of a polynomial ring in 2 variables. You have a quotient of a polynomial ring in 1 variable quotient, 2 variable quotient. And then what I can do is I can sum them all up. And this is the underlying vector space of the corresponding arc algebra, in this case H2. So one important point is I should mention this is only as a vector space. So this equality is not as an algebra. It's not a direct sum of these polynomial rings. It's this is just the underlying vector space. So the multiplication is actually really interesting. So let me explain how this works in an example. So let's say I want to multiply an element in here. Let's say in this summand with an element in this second summand. So what I would do is I would draw the corresponding pictures, right? So for the first summand, I have this picture, and for the second summand, I have this picture. I stack them on top of each other. And then there are 2 things that can happen. So maybe the pictures in the middle kind of match up in the sense that one is just a reflection of the other one, in which case I'm going to do the following, okay? So if they match up in the middle, I'm going to construct a sequence of surgeries where I just replace cup-cap pairs by 2 vertical lines. So here I'm going to do this with the first cup-cap pair, then I continue. And at the end of the process, I just have a bunch of lines in the middle of the diagram, vertical lines, at which point I'm going to collapse the picture and I get back my peanut. So what this construction does is basically it tells you where the result of your multiplication should be in, okay? So if I, let's say, so again, so I wanted to multiply something in this summand with something in this summand. So what this now tells me is the result, whatever it is, should actually be back in this summand here. So now the question is, okay, what is it? So, and then you can maybe even guess what's going on now. So, I mean, in each step here in this process, I only have a bunch of circles. So what I'm going to do is I'm going to assign, of course, the quotient of the polynomial ring in 3 variables to the first picture because I have 3 circles. Then I have a quotient of polynomial ring in 2 variables, quotient of polynomial ring in 1 variable. And then if you look at this carefully, since in some sense I'm doing this replacement, like replacing a 0 resolution by a 1 resolution each step, I again have this situation where exactly one circle either splits or two circles merge. And this means I have maps connecting these polynomial rings, just like in the construction of Kovanov homology. And this actually gives me the map. Okay, so what I can do now is I can identify this quotient of a polynomial ring in 3 variables with this tensor product. And so this first tensor factor corresponds to the original first summed up here. And then this guy corresponds to the summed up here. And this is actually the multiplication map that you have in this algebra. And what you get is a nice unital associative algebra, and everything can be done in the graded setup, which I'm completely ignoring in my talk here. So this is exactly this arc algebra. Yes, question?
Do the diagrams have to match up like that?
Oh, yeah, that's a, oh, thanks. So yeah, the question is, do the diagrams have to match up? So thanks for reminding me about this. So if they do not match up, the multiplication is 0. Okay, so in many cases, the multiplication will be 0, and I'll try to say something about this in a minute. Why this is actually not so unnatural. It's actually quite natural. But yeah, if they don't match up, you know, the product will be 0. Yeah. Okay. So let's move on. Anything else? Okay. So right. So I explained this arc algebra a little bit. So now there's one last thing in my title, which was these Springer fibers. So here's a result due to Khovanov. So Khovanov actually studied the center of this arc algebra. And what he figured out is that the center is actually a cohomology ring of a certain algebraic variety called a Springer fiber. Okay, so this is this B sub n comma n. So this is yeah, the cohomology of some algebraic variety. So I should tell you a little bit about what's going on here, because this is probably not very familiar to many of the people in the audience here. So what's going on here? Okay, so the Springer fibers, how do you construct this? So it starts with a nilpotent matrix. So let's say you consider m by m matrices, everything is over the complex numbers here, and you fix a nilpotent matrix X. So what you can do then is you can go to the flag variety here inside Cm. So I look at these nested subspace inside C to the m. And so how does this nilpotent here come into the picture? So I put the nilpotent into the picture by requiring basically that each vector space here in my flag has to be fixed by the nilpotent. So if I apply the nilpotent to the ith space, I have to end up in the ith space again. So this is a very important algebraic variety in geometric representation theory. And it's kind of interesting that you can kind of connect this to this not homology stuff. So let me maybe, yeah, before I move on, let me introduce some more notation here, because if you recall, like on the previous slide, I had this guy. So the question is, what does that mean? So what actually happens here is if you look at nilpotent matrices, right? So in linear algebra, we kind of learn how to classify nilpotent matrices up to conjugation, and they're actually given by the Jordan normal form, right? So every nilpotent is basically conjugate to something in Jordan normal form, which for a nilpotent means eigenvalue 0, right? So I get all these Jordan blocks here. And let's say 1's up here. Okay, this is not a very good square, but yeah, you see what I'm getting here. And then the only thing that I have to kind of record in order to specify a nilpotent is basically I have to give you a partition, right? So if so any partition of M, so this is an M by M matrix, is going to give me like one of my nilpotent matrices up to conjugation. And why is that important? Because well, the Springer fiber actually just depends on the Jordan type of this nilpotent. So this J of X means the Jordan type. So if the Jordan type is some partition lambda, then up to isomorphism of algebraic varieties. So the Springer fiber actually only depends on the partition. And this is what explains this notation. So what I'm doing here is basically I'm looking at a partition. So I don't know how familiar you are with this if you are a topologist, but I draw a partition using these Young diagrams. It's just a bunch of boxes. So this is basically yeah, the partition corresponding, let's say, to n boxes in the second row and n boxes in the first row. So this is a nilpotent in the language of nilpotent operators. This is 2 Jordan blocks of the same size. Okay, so these are the Springer fibers that we're looking at here. So very special Springer fibers, just 2 Jordan blocks, and they have the same size. So this is what's going on here. So let's see, let me clear all of this. Okay, so as I said, these things are actually quite important in geometric representation theory, and here's the reason for this. So if you look at the cohomology of a general Springer fiber, you fix the Jordan type, you can describe a cohomology of this, and this is actually just a quotient of a polynomial ring in m variables. And this ideal here, so this is called the Tanesaki ideal. So this can be described very explicitly in terms of certain elementary symmetric functions. And the reason why this is important is because you can now construct irreducible representations of the symmetric group. Okay, so these cohomology rings, they carry an action of the symmetric group here. And for the purposes of my talk, I want to think of this as the Hecke algebra of the symmetric group specialized at q equals 1. So what's going on here is basically this Hecke algebra is basically a q deformation of the group algebra of the symmetric group. So if you've never seen this before, don't worry about this, but I think we saw it in Radmila's talk, at least briefly. So it's an important object. If you don't know what this is, just think of this as a q deformation of the group algebra. If you set q equals to 1, you recover the group algebra. So this is why they are so important in geometric representation theory, because you can construct irreducible representations. Okay, so now, any questions about this? Okay, so then let's go back to this. So the center of this arc algebra is actually the cohomology ring of a very special Springer fiber, the one with 2 Jordan blocks of equal size. And here's an interesting generalization of this result, which was done by Katarina and Ben Webster. So they actually extended this result and geometrically constructed the entire arc algebra using irreducible components of these Springer fibers. So these Springer fibers, they're actually very interesting algebraic varieties. So they're not smooth in general. So they decompose into many irreducible components, and they're actually, these irreducible components themselves are kind of difficult to understand. So yeah, so if you take a Springer fiber, it's basically a union of easier subvarieties, okay, which are then irreducible. So this is what's going on here. And what so Katarina and Ben did is basically they looked at pairwise intersections of these irreducible components of this Springer fiber, which already appeared in Khovanov's work here. And then if you take the direct sum of this, you recover actually the arc algebra, and you can construct the multiplication using some convolution product on this on this vector space. And maybe there's one thing I should, maybe some comments about this. So what's interesting here is if you look at the Springer fiber, so the irreducible components here are actually labeled again by these cup diagrams. Okay, so these cup diagrams or these crossingless matchings, they are in one-to-one correspondence with the irreducible components here. So this may be one observation. And then maybe the other observation is, why do you want to do this? And there's actually a nice like story behind this. So originally, I mean, this result is like 10 years old. So at that point, people did not really understand the connection between like the original Kovanov homology and the symplectic version due to Seidel and Smith. And what this literally is, this is a toy model for a Fukaya category. So this is, some of you might want to think about it like this. So you can think of these irreducible components as Lagrangians in some bigger variety. Usually I think this is some Slotowski slice. And so these cohomologies of these pairwise intersections, they're like your Lagrangian Floer cohomology groups for these two Lagrangians. Okay, and the product on this algebra is, you can think of this as the composition in your Fukaya category. So this is also why, if things don't match up, right? Remember, so for example, if I have something like this, let's say I want to multiply something in this component with something in this component. Let's say this is a C and this is a D. And let's say these guys are not the same. Then the product was 0, right? And this is sort of, it mimics this fact that I have a category here. So for a category, the target of my first home space should be the domain of my second home space. And if you really think of this as a Foucault category, so it makes actually sense. Okay, so this may be a comment which goes into this direction, but I don't want to like beat this to death. There's an interesting reason why people want to study this. Okay, great. So now this is basically the background story of things that are known. So what I want to do now is basically generalize this to the odd setting, okay? So this is what we did in this work with Jens, Eberhardt, and Naisse. So let me talk about this. So what I'm basically going to do is on the right side here, I'm trying to generalize everything that we have on the left for this odd setting. Okay, so the first question is the same, right? So you have odd Kovanov homology and you want to extend this to tangles. So this was successfully done in recent work by Naisse and Putyra. So that's good news. And what's going on here is an important ingredient in these constructions are so-called odd arc algebras. So in the notation, I'm just going to put this O here to indicate that this is the odd arc algebra. So this was actually originally constructed in Grégoire, so Naisse's master's thesis under the supervision of Vaz. And so this is a very interesting algebra. So what happens here is so I don't want to get into the technical details of this, but what happens is you basically mimic the construction that I showed you for this algebra, but you do everything with these exterior algebras and these maps that come from these exterior algebras. And what happens is you get certain signs here, okay? So the idea in constructing this is very similar to the original arc algebra, but you get these weird signs. And it's actually so weird that at the end, this algebra is not going to be associative. Okay, so this is a big issue in some sense. So these signs kind of destroy the associativity of this algebra. And this is also like why it is so difficult to extend Kovanov homology Kovanov homology for tangles to odd Kovanov homology for tangles, because the underlying algebra is not associative, and then you can't do tensor products and stuff like this over non-associative algebras. At least it's kind of difficult to make sense of this. Okay, but anyway, so these things are done. We get like a kind of slightly weird odd arc algebra. And there is a result similar to Khovanov's result here on the center of this. So instead of considering the center of this odd arc algebra, I have to consider something called the odd center. So this is kind of like the center. So things, you look at elements which commute when you multiply them, but they only commute up to a sign, okay? And the sign kind of depends on the parity of certain elements. So what happens here is you look at something called the odd center, and then you can actually identify this with something called the oddified cohomology of the Springer fiber. So let me maybe explain a little bit more what's going on here on the right side. So what's the oddified cohomology of a Springer fiber? So this is a construction which, so let me go back to the Springer fiber slide. So this is a construction which goes back to Aaron Lauder and Heather Russell. So, and it is as follows. So basically you look at the usual cohomology ring of the Springer fiber. And if you want to oddify this, what does that mean? Well, this oddified cohomology ring is essentially obtained like this. So you take this polynomial ring in m variables, and you actually replace this by a free algebra in these generators x1 up to xm. And then you mod out by this ideal, which basically tells you, well, I'm going to make these generators anti-commute. Okay, so then you're back to your signs. And what they also do is they sprinkle certain signs in this Tanesaki ideal, which is given by certain elementary symmetric functions. And this is how they basically oddify this cohomology ring. And so the reason why they do this is actually what they do in this paper is kind of an analogy to what happens on the left side. They actually get representations of the Hecke algebra, but now specialize at q equals -1. So what corresponds to the oddification on the representation theoretic side is basically replacing the Hecke algebra specialized at q equals 1 by the Hecke algebra specialized at q equals -1. So this was originally what happened in this paper. And so if you think about this, so when we started this project, so what always bothered me about this construction is that it is kind of, it seems ad hoc, okay? And there's no geometry. So do you really want to take a variety, take cohomology, and then modify the cohomology ring? It seems kind of unnatural, right? So what you really want to do is you want to modify the space and actually apply the usual cohomology functor to this. So this is what was kind of like the starting point of this. So I was talking to Grégoire about this, and it was kind of something that was bothering us. So question, can we find a variety such that when we take cohomology, we get this modified cohomology ring naturally? Thing is, it turns out that this is not really possible. And the reason for this is that if you look at the modified cohomology ring here, so if your nilpotent element up here has more than 2 Jordan blocks, what happens here is this modified cohomology is not a ring anymore. So this may be comment number 1. So this ideal, because of all these nasty signs that you get, the ideal that you mod out here is actually not a two-sided ideal. Okay, so you look at you have certain generators here, and you have to either decide, do I look at the right ideal generated by this or the left ideal generated by this? And in contrast to the left side, you have to make a decision, and you're not going to get a two-sided ideal in general, which makes this kind of impossible to realize this as a cohomology ring, right? Because a cohomology ring is a ring. However, in the 2-row case, which is the case which is important for Kovanov homology, right? Remember this n comma n, 2 nilpotents of equal size, this is actually a ring. Okay, and so this question makes sense, and it has a positive answer, okay? So what the first step in this project here was to actually find a space whose cohomology is naturally the modified cohomology ring in the 2-row case, okay? When the nilpotent has 2 operators. In general, it's just hopeless because of this remark that I just made. So yeah, let's go back to this slide and add this result. So this is, as I said, joint work with Jens Eberhardt and Grégoire Naisse. So this modified cohomology defined by Lauder and Russell is actually just a cohomology ring of the real points inside the complex Springer fiber. So what you're basically doing is you're looking at flag varieties over the real numbers, okay? And this kind of turns out to do the job, okay? But keep in mind, again, this is only for nilpotents with 2 Jordan blocks. It can be generalized, like they don't have to have equal size. So the fact that I have n comma any is just for the for simplicity in this talk, but you can do it for any 2-row partition. But it's impossible to do it for more than 2 Jordan blocks because the left side is not a ring. Okay, so this is the first result, and maybe some motivation for how do you come up with this, right? So how do you come up with this answer? Why should real points in some complex variety be the answer to this question? Well, if you think about this, let's go back to the original construction of Kovanov homology, right? So at each vertex in your Kovanov cube, you have this quotient of this polynomial ring here in these n variables. And if you think about what this is as a cohomology ring, well, this is just a cohomology ring of n copies of CP1, right? And so if you think about this, what's CP1? Well, CP1 is kind of the easiest flag variety that you can think of, right? It's like lines in a 2-dimensional space. So, right, so the idea was kind of like to yeah, look at the odd version and see if we can kind of realize the exterior algebra as something similar. And then you see, well, what's the exterior algebra? Well, that's just a cohomology ring of a bunch of RP1s, right? So then what's RP1? Again, it's a flag variety, right? It's lines in a 2-dimensional real space. So the idea is kind of, okay, well, it seems like we have to replace, in order to pass from the original theory to the odd version, we kind of have to replace complex numbers by real numbers, or complex varieties by real points inside a complex variety. And it actually worked, okay? So this is the central idea. Just look at the construction of Kovanov homology, and you realize what seems to be the natural thing to do, and it works. Like you can extend this to flag varieties, to like these Springer fibers, to the irreducible components, and it all works out. You just have to pass to real points everywhere, which is kind of nice. So it gives you a very nice geometric idea why odd Kovanov homology exists. It's literally like the fact that you can pass to real points like naturally gives you all of these signs, which are kind of ad hoc, if you think about this. Okay, so one other result that we have here is we're going to construct this odd arc algebra in analogy to this Straubel-Webster result using intersections of real points in these irreducible components. And again, yeah, this convolution algebra that you get here turns out to be the odd arc algebra, which is up here, the ingredient to construct odd Kovanov homology for tangles. Okay, so it's the same construction, but again, just passed to real points. Okay, so then maybe one thing I want to say is I want to kind of now maybe look at what these kind of varieties look like a little bit. Unless, are there any questions right now?
Yeah.
Yes.
The homological grading in the cohomology ring, do you have to like stretch it or anything?
Oh yeah, exactly. So right, that's a good point. So the degree is kind of off. I agree. So you have to double it.
Okay.
Right? Yeah, that's right. Yeah, it's a good point. Yeah, but since I'm ignoring gradings here, but yeah, you're right. You have to double it in the real story, in the odd version. Yes. Anything else? Okay, so maybe I should tell you a little bit more about these Springer fibers and what they mean from a topological point of view, because this is probably what you know least about, okay, at this conference. So let me talk a little bit more about these Springer fibers and what they look like somehow from a topological point of view. Okay, so kind of like we saw here, right? There is an irreducible component of a Springer fiber here, of this Springer fiber with the two Jordan blocks of equal size for every crossingless matching on two n vertices, okay? So let me construct a topological space given a matching here. Okay, so what I can do is I fix like a crossingless matching on n points. So let me actually work out a full example here. For simplicity, let me take n equals 2, okay? Because that's what we already discussed in the context of this arc algebra. So again, here I write down my two elements, right? What are all the crossingless matchings on 4 vertices? Well, I have A, I have B, so these two guys. And now what I can do is I can fix one of these diagrams and I can assign a certain manifold to this, which I'm going to label by S subscript A. And what is that? So this is a certain submanifold in a 2n-fold product of the one sphere with itself. Okay, so this is just a product of this one sphere with itself, and the 2n is exactly the number of endpoints here at the top of my cups. And what is it? Well, here's the manifold. Okay, so you basically just look at all points in S1 10 to the power S2n. So I have 2n spheres, and then I identify coordinates according to my arcs. Okay, so if there's a cup here connecting the first and the second vertex in my picture, then I'm going to identify the first two coordinates here in this construction of this manifold S sub A. So actually, here it is. Okay, so what you end up doing here for the first diagram is, well, everything lives inside S1 to the 4th power, so a 4-fold product of this sphere with itself. And then this diagram tells you I better identify the first two coordinates, and then I better identify the last two coordinates, and then I have a remaining choice of an element in S1 for my X and for my Y. Okay, so what actually happens here topologically, this is literally just a torus, right? It's S1 cross S1. So similar, you can do something with this guy. So, well, there's a cup connecting the first vertex and the last vertex. So I identify the first and fourth coordinate, and then I also identify the second and third coordinate. And then again, I have a torus, right? And so here's now what's going on. So why do I care about these manifolds? Well, so here's one of the results, which is also in the paper. And it's kind of a key result in order to construct this algebra. Because in order to construct the algebra, we have to understand these real points in the irreducible components. And this is what this theorem kind of does. So what this says is that I can now look at all these crossingless matchings here, construct these corresponding manifolds, like which are very explicit, right? It's basically just explicitly given submanifolds inside like a product of S1s. I can take the union okay? And then this is actually homeomorphic to the real points inside the Springer fiber. Thing that most people do these.
I don't know if anybody can hear me, but we lost audio and the screen.
Yeah, we hear you. I think his computer got disconnected, but his tablet is still on. Should we send him an email to let him know, or?
I don't really know what's happening. Maybe I'll call Dave. Just a second.
Hello.
Make the full screen.
Okay.
Okay, wait, where did I lose you guys? Can you maybe quickly let me know?
You're good. You're good. You're good, Peter. Okay.
It was about here. Where you are on the screen. We heard that. You started.
Oh, so is this okay? Do you have
Yeah,
questions about
this
this?
is okay. We saw that.
Okay, so then I guess the next one was the theorem here, which
Yeah.
basically says that, right, so we have this, so if I take the union of all of these guys inside this product of the spheres, this is literally the real Springer fiber as a topological space, okay? So this gives me some nice model to work with these, instead of, if you don't like flat varieties, which I think many people here would probably prefer this sphere picture, okay? So does that make sense? Is everyone on the same page now?
So these are like half-dimensional tori inside of tori, and then you're taking some.
That's right. Yeah. So this is like a diagonal embedding of a sphere inside a product of two spheres. Yeah. Okay. So, anyways, so let me maybe tell you what this what the real points are in the Springer fiber for 2, 2, okay? Because I can now work out this picture completely. So in order to understand the union, I kind of have to understand how these things are clued, right? So individually, I know that I have 2 tori. So the intersection is easy to compute. I mean, look at this. points inside the intersection? Well, I mean, the first two coordinates have to be the same. Well, if a point is also in S sub B, well, the second and third coordinate have to be the same. So now I have x, 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 x. So this is just a sphere topologically, okay? And now if I put them together, I actually get this. So if you were ever wondering what the real points look like inside the Springer fiber for the nilpotent given by two Jordan blocks of size 2, then you get something like this. It's like a figure 8 cross S1, okay? Does that make sense? So this is what's going on. So these are really the varieties that are like key to this odd Kovanov homology if you try to understand this geometrically. So I thought this is a nice picture. Okay, great. So any questions about this? Okay.
Oh no, it's starting again.
Keep going. Just keep going. Power ahead.
I don't know. Let's wait. I'm back, right?
You're there.
You are, but not the screen.
Okay. Do you see the screen now?
Yeah.
Okay. So let's hope we can finish this now. This is the last slide. Okay. So right. So originally I mentioned, so I'm interested in these arc algebras because they have, I mean, they connect to interesting representation theory. Okay. So originally they were defined by Kovanov in the context of link homology, but they connect to interesting representation theory. So that is maybe the first point here that I want to make. So there are two things I kind of want to discuss real quick. So if you take the original arc algebra here, which you can realize as this algebra given by these pairwise intersections of these irreducible components with the convolution product. So then originally, of course, the reason why this is interesting is because it gives you Kovanov homology for tangles, okay? But the point is there's much more, okay? So if you look at this work by these other people that I mentioned, so for example, by Katarina, so Katarina Stroppel, so she connects modules over these arc algebras to Lie theory in the sense of some category O. So if you look at slight modifications of this arc algebra, so the combinatorics still are the same, but you have to modify it slightly. You can connect this to a certain parabolic category O for the general linear Lie algebra. So this is basically infinite dimensional Lie theory. So maybe I'm not going to beat this to death. If you have questions, I'm happy to talk about it some more. But yeah, you can connect this. So this arc algebra describes much of the representation theory of certain Lie algebras, or infinite dimensional representation theory of certain Lie algebras. So then this is actually the same thing. So you can also look at perverse sheaves on Grassmannians of n-planes inside a 2n-dimensional space. So if you look at this, it's the same as category O, but in a more like slightly more geometric flavor. So these arc algebras actually describe these categories of perverse sheaves for Grassmannians. So then this is more like diagrammatic algebra. So this is it's a Brouwer algebra. So this plays an important role in certain Schur-Weil dualities in representation theory. And you can describe certain decomposition numbers, like important representation theoretic properties of these modules over these Brouwer algebras using these arc algebras. And one final thing, which is interesting to many people, is the connection to Lie super algebras, or in this case, the Lie supergroup GLRS. And you can actually describe the finite dimensional representation theory of this Lie supergroup using the combinatorics of these arc algebras, which is quite interesting and kind of non-trivial. I mean, there's a lot of work going into this by John Brandon, Vera Zerganova, and then also, like, again, work by Stroppel and Brandon. So this is extremely rich, also to a representation theorist. And maybe I should mention that now we have this O like this odd version of the arc algebra, and we kind of know that I have to put an odd here in front of Kovanov homology to kind of generalize this picture. But the point is now there are a lot of question marks here, okay? And so one interesting direction would be to kind of like push this into a more representation theoretic direction and see what these odd arc algebras and real points and Springer fibers have to say about representation theory. So the second point that I want to make is more like a topological thing. So let me talk about this real quick. So what we show in our work with Jens and Grégoire is that if you take a Springer fiber for a nilpotent which has at most 2 Jordan blocks, right, you can take this oddified cohomology defined by Lauder and Russell, and you can realize this as the real points, cohomology of real points in some Springer fibers. So this works up to 2 rows, and it's part of this paper, but there's no hope that this works. Like I said before, there's no hope that this can be generalized beyond 2 rows, because then this guy here is not a ring, okay? So if lambda has more than 2 rows, then these guys can't be isomorphic. I can still look at the cohomology of these Springer fibers, but they can't be the same. This is naturally a ring, right? It's a cohomology ring, whereas this guy does not have a ring structure. So what happens here is kind of an interesting thing. So our geometric picture kind of coincides with this modified story here by Lauder and Russell. But once you go to more than 2 rows, they diverge, right? You get a different picture. So what happens here is what comes out of this paper with Jens and Grégoire is actually some new structure, which is certainly not the same as what Aaron and Heather did in their paper. And so this is like a little bit, it's not a conjecture, I wouldn't say it's a conjecture, but maybe what would be nice is if there would be some hope to get odd categorifications of SLN invariants for n greater than 2 out of these like new varieties here, okay? This is like an open question. I mean, we have odd Kovanov homology, and Kovanov homology is kind of the SL2 story of this from a representation theoretic point of view. So what happens for SLN where n is greater than 2, right? And at least here's something interesting going on, which is new, right? Which does not coincide with what people have looked at before. So maybe that's a good point to stop. Do you have any? Yeah.
Any questions for others?
So when you said at most 2 rows, would that mean that if I have like one big Jordan block and one small one, this will still be a ring? Because like, okay, so what I'm saying is I don't need to glue tables that are necessarily all
when things are
right,
all
as long as I'm doing only 2 tangles together and the number of points on the bottom and top match, like does that is there still a good meaning for that?
Can you repeat that question for everyone?
Okay, wait. So maybe before let me right. So the question was about the 2 rows. Wait, can you maybe say this again, because I was busy like trying to like figure out my pen. Yeah.
Yeah, I mean like okay, so you're looking at the n.
Yep, that's right.
But you can have like n plus 1, n minus.
Right. Okay, so let's maybe stop here real quick. So yes, so Melissa was asking about the partition. So all of this works. So what do I mean by this? Okay. Wait, hold on. What? Oh wait, no, I got it. Okay, so Melissa was asking about this. So lambda at most 2 rows. So what this means is anything that has 2 rows is fine. So what you can do is you can look at partitions which look like this. And then at some point you can add stuff here. So let's say this is K boxes and this is, let's say, I don't know, n minus K, okay? So this completely works. And it's sort of part of the paper, but I didn't discuss this because the combinatorics gets slightly more involved. You can't just describe this by cups. Okay, there's more that you have to do. Actually, you have to do some rays, which you might have seen before. But for time reasons, not to make it too complicated, I didn't cover this case, but it is covered under what we do, okay? So this works. So you can do what you wanted to do, like n minus 1 and n plus 1, for example. You can actually do this for any K boxes at the bottom and any n minus k boxes at the top. Yes, and then there was something about the tangles. Okay. Yeah, so this is what's going on. So of course you can look at nilpotents, yeah, which have two drawdown blocks, but they can have any size. The important thing is I only have two drawdown blocks. That's what I mean by at most two rows.
So I had a question, if you can hear me.
Yes.
Okay, thanks for the talk, first of all. Secondly, I have a very general question. Do you find any interesting phenomena in odd Kovanov homology, like extra structure on odd Kovanov homology that you don't see in sort of even Kovanov homology? Like, for example, I think, if I remember correctly, you mentioned that the odd arc algebra is not associative, but can you perhaps fix that by, I don't know, defining some infinity structure on it or something of that sort?
Yes. So, I mean, did you hear the question? So it's about extra structures in odd Kovanov homology, things that you see in odd Kovanov homology, which you do not see in the regular setting. And so, right, so this algebra, right, so this algebra is not associative, right? This is what you said. And I cannot fix this using an A infinity structure. So I'm not an expert on this, but Grégoire, I mean, he knows a lot about this. So he said it's not an A infinity structure, but what you can do is it's somehow like a quasi algebra, whatever that means. It's a quasi algebra created by a groupoid. So don't ask me what that means. But apparently it's enough structure to kind of look at quasi-bimodules and things like this. So you can actually do this extension of odd Kovanov homology to tangles. So maybe you should Google, like look at this paper again. I personally haven't looked at this in detail because it seems kind of technical to me. But there is like actually some theory around how to deal with the non-associativity. And there's some theory of quasi-algebras. That's what they call it. Right, so there is, in this sense, there are new phenomena appearing, definitely. But like on the Kovanov homology itself, I don't know. So for example, maybe let me say something about this. So what happens here is, for example, if you look at these cohomology rings of these real points in the Springer fibers, what happens is you get torsion, for example. This is something that does not really, which does not happen in the usual case of complex Springer fibers. So the question is, what does that mean? So there are some things which are different, but yeah, but yeah.
Yes, I was asking. I was asking because I'm looking for some explanation for phenomena that, so the kind of Kovanov homology over Z mod 2 coefficients is kind of special when compared to other coefficients, other characteristics. So I was wondering whether the explanation for those phenomena in even Kovanov homology over Z mod 2 might be explained by something happening in odd Kovanov homology, where you see more structure there, and then you can, yeah.
So yeah, I don't know if you see more structure. So from my point of view, it's different structure in some sense, right? So it's not that you see more structure, it's just different. I mean, it's also like reflecting the fact that Kovanov, like odd Kovanov homology distinguishes links which regular Kovanov homology does not distinguish, and vice versa. So I think they kind of complement each other in the sense that, so it's, I don't know, but my answer is I don't see anything, or I can't explain any phenomena in the usual Kovanov homology using odd Kovanov homology. I don't have an example of this. And that's maybe a disappointing answer, but yeah.
Okay, I should look into quasi-algebras and created by groupoids.
Maybe that's probably a good idea.
Okay, thanks for the talk.
All right, so let's any more questions for Arik Wilbert. So let's thank him again for his great talk. We'll come back in 10-15 minutes. We're like in the talk session.
Canoers, just write your name here so you don't get forgotten. And the plan is to be at the 1 o'clock at the Georgia Center Hotel lobby entrance side, like there, you know, there's not where the shuttle dropped you off in the parking garage, just to the other side of the Georgia Center where that's like the actual, there's a little drive-through too. So just leave this right here. Oh, and I recommend that canoers grab a, if you don't have your own water bottle.
Will you be
wanna bring
stumbling
some,
forward?
There's some store-bought water bottles in the lounge room, and you grab a couple of those, take with you.